Hello everyone and welcome to my steel design tutorial. In today's steel design tutorial, I'll be showing you how to design a restrained beam using Eurocode free. But before I begin this tutorial, I'd like you to hit the like button and subscribe for more civil engineering tutorials on my channel. And if you're interested in looking for Eurocode free references, feel free to check out the links in the description box down below. So without further ado, let's get started. So we have the basic information of our beam over here. So we have a slab of 140 millimeters thickness with a assumed density of 2,400 kilograms per cubic meter, an imposed load or imposed action of 7 kilonewtons per square meter, with a beam span as shown in this diagram of 7.2 meters, and the beam spacing is 3.6 meters. So imagine another 7.2 meter long beam, 3.6 meters into this view, for example. So now let us focus on the things that we need to design for. So first off, we need to do cross-section classification, then determine the shear resistance, the bending resistance, and finally the deflection. And now let us move on to the loadings. So permanent loads are calculated as follows. So we have the density of the concrete here, and this is G, and this is the thickness of the slab multiplied by 3.6 meters over here. So we get this value right over here. And for the variable loading, it's just the value itself multiplied by 3.6 meters, and we get this 25.2 kilonewtons per meter. And we're using a unit of kilonewtons per meter because we are assuming a uniformly distributed load. And so this is the ULS combination over here. So the dead load is multiplied by 1.35 and the live load is multiplied by 1.5. Design ultimate moment is going to be calculated with this equation, since we are assuming a uniform distributed load over here. So WL squared over 8 will be used, and the design ultimate moment will be 357.7 kilonewton meters, and the ultimate shear force is calculated as WL over 2, so you'll get 194 kilonewtons over here. So let's move on to the initial sizing. So I have 2 points over here, so I'll be adopting an S275 steel grade with material thickness not exceeding 16 millimeters, and I will assume that the cross section is class 1 or class 2 in bending. So this equation here for the plastic modulus, this will help us determine the initial sizing of the beam. So this equation will apply to class 1 and class 2 steel members over here. So all we need to do is rearrange this equation here on the left into this form, so that we can actually determine the required plastic modulus and find a steel member that is going to satisfy this value over here, this 1,300 centimeters cube. So for this case, I'm using universal beam 457 by 152 by 67 with a plastic modulus of 1,450 centimeters cube. And the maximum component thickness is the flange with a thickness of 15 millimeters here. So for this universal beam, the thickest part of it is the flange, and the flange thickness is 15 millimeters, so it's still less than the 16 millimeter requirement over here. So Fy is 275. If the universal beam had a plate thickness that exceeds 16 millimeters, then the value of Fy will not be 275. I'll be talking more about that in another video, so stay tuned for that. And now let's proceed to the cross-section classification. So we need to calculate epsilon over here. Epsilon is equal to square root of 235 divided by Fy. In this case, Fy is 275, so epsilon is equal to 0.92. So from this table in Eurocode 3 for class 1 flange in compression, this flange slenderness ratio must be true, And for a class 1 web in bending, this web slenderness ratio must be true. So to calculate CF and CW, use these two equations. So I've already calculated CF and CW. You should get 62.2 for CF and 407.6 for CW. And this is the flange slenderness ratio over here, so it's less than 9. So the flange is class 1. And this is the web slenderness ratio, and it's less than 72, so it is class 1 as well. So as a whole, this cross-section can be considered as class 1. I'll be making another video on the different classes for beams, so stay tuned for that as well. And now let's determine the shear resistance. So we need to use this equation over here. And AV is calculated using this equation over here. So AV is the shear area over here. So you need to know the area of the section. You can get that from the Steel Blue Book. The link is in the description. Basically, in the Steel Blue Book, you'll get the area in centimeters squared. So we need to convert it to millimeters squared over here. And the breadth of the member is 153.8 millimeters. The flange thickness is 15 millimeters. The web thickness is 9 millimeters. And R over here is the radius of the member, which is about here, R. And again, TF, which is the flange thickness. So you should get this value of 4,387 square millimeters over here. Plug in this value into this equation. You should be able to get 696.5 kilonewtons, so it's far greater than the design shear force. And now we need to quickly check for shear buckling in the web by using this equation over here. So HW is equal to H minus TF. So this is the height of the web over here. So the height of the web is 428 millimeters over here. Divided by the thickness of the web, we will get 28.5. And then if we compute the right hand side over here, we get 66.2. So since the height of the web to web thickness ratio is less than 66.2, shear buckling is avoided and the section is okay under shear forces. Moving on to bending resistance. So this equation over here is similar to the one over here. So now we just need to key in the values of plastic modulus over here and the yield strength of our member over here, and gamma M0 is just 1 in this case. So we will get 398.8 kilonewton meters of bending moment resistance. So this value is much greater than the design bending moment. So this section is okay in bending. And finally, for the deflections, for beams carrying plaster or other brittle finishes, L over 360 is the equation that we'll be using. So we have a 20 millimeter maximum deflection over here. So the allowable deflection would be 20 millimeters over here. And since our beam is a beam that is uniformly loaded, we will use this equation over here, 5WL to the power of 4 divided by 384 times bending stiffness over here. And you should get 0.0145 meters or 14.5 millimeters here, which is less than 20 millimeters. And therefore, the deflection is within limits over here. And thank you for taking the time to watch this tutorial. If you enjoyed this tutorial and found it useful, like this video and share this video and subscribe for more civil engineering tutorials. And if you're looking for more Eurocode free reference textbooks, feel free to check out the links in the description box below. And as always, stay safe, keep learning, and goodbye.